In this video, I'll step us through a derivation of the Lorentz equations. So we'll start with, again, a two-observer space-time diagram. And the situation is, suppose we have some event A in space-time, and we know the coordinates for this in the primed frame. So remember, to get to the to read the primed frame, we drop not perpendiculars but parallels. Okay, so these two lines are supposed to be parallel, these two lines are supposed to be parallel, and I feel like I did a pretty good job with that, all things considered. All right, so the picture here is that we're given, we know t prime and x prime, and we would like to know, given that, what are t and x? So we know how to just, we could just read it right off the graph, but what if we wanted a formula for that? That's what we're working towards here. All right, so let's see. So we know x prime. So x prime, that would be this length on this graph. And maybe, because I'm referring to this event A, let me put A subscripts there. All right. So x prime, that's this length. That's how we would visualize x prime on this chart. That's a distance from there to there. And let's see, the time for this event, we'll go here and we'll read it off of this axis. So this, from here to here, this is t prime of A, this is x prime of A. All right, so let's focus on x for the time being. But actually first, let me note that this length and this length are the same, right? Because this is a parallelogram, it's parallel, parallel. So this is t prime A, this is also t prime A. And I won't draw the arrow here because this is starting to get pretty messy and cluttered. All right. So now let's think about converting these x prime t primes into x and t. Remember, we do that with gamma. So if this is x prime A, this is, I'm going to call this just a distance gamma x prime A, like that. Okay. And this is going to be gamma t prime A. Because the tricky thing here is that the units, the calibration for the blue axes, the moving reference frame, is not the same as for the black at rest frame. All right, so I would like to know the x coordinate for A. And so, well, I could read that off the graph. It's going to be this plus this distance. How do we think about that? All right, so let me draw a line down like this. So I claim that the x coordinate of point A is this plus that. All right, so what are we going to do with that? Let's see. All right, so this distance is the same as that distance. And let's see, what do we know? Well, we know this distance is going to be the same as that distance, right, measured in the x frame. So this here, I'll draw it like that, maybe this is going to be gamma t prime A. So, but I don't want this side, I want that side. And we can figure out this side as follows. So we're looking for this length or that length. And I'm going to call that, I don't know, x question mark. Couldn't figure out what to call it. Because that's an x. We want to know what that x is. So let's call it x question mark. All right. So we know the slope of this, or put another way, we know how fast the blue frame is moving with respect to the at-rest frame. It's moving at a speed of beta. And so that tells me that, that I can use it to figure out what x question mark is. So beta, it's a speed. It's going to be a delta x over a delta t. So delta x, oh hey, that's the thing I want to figure out. Delta t is given by this, gamma t prime a. So I can solve this for x question mark. And I should mention, just so that the picture is clear, remember this is the world line of Beowulf's clock moving at a speed beta. This would be the world line of another one of Beowulf's clocks, also moving at a speed of beta. Or you can just say, look, these two things are parallel. This is moving at a speed of beta. That's moving at a speed of beta also. All right, so let's solve for x question mark. X question mark is beta gamma t prime a. And then I can say, all right, I know what x is. Right? This is, or call this xa. This is the x coordinate of event A in the unmoving frame, in the at-rest frame. And it's just this plus that. So I guess I'll write this here. So xa is gamma x prime a plus beta gamma t prime a. And aha, this is what we're after. Given coordinates in the moving frame, I figured out what at least the x coordinate is in that rest frame. So the next thing we need to do is figure out the t coordinate in the at-rest frame. So we've figured out a formula for xa, the spatial coordinate of event A in the at-rest reference frame. What we need to do now is figure out a similar formula for TA, the time coordinate of event A in the at-rest frame. The good news is we've already done a lot of the work to do that. So here we have this event in space-time, and if I wanted to read its time coordinate in the unprimed frame, well, I just go over here. So this is the time coordinate that we're after. This length is going to be the same as that length. So I'm looking for this length, and I've already got a chunk of it. I know that this is gamma t prime a. So I just need to figure out this little part, which I've called t question mark. So we can figure out t question mark by looking at this triangle and noting that the slope of this line is beta. The slope of this line is 1 over beta, and the slope of this line is beta. So let's use that fact. All right, so the slope is beta. And so rise over run, that's the rise, t question mark. This length, the run, is gamma x a primed. So then I can solve, oh, I'm sorry that you couldn't see that. So then, so what I said was beta, that's the slope, rise over run. Rise is this distance, t question mark. Run is that, gamma x prime a, and so then I can solve for t question mark. It's just beta gamma x prime a. So then we can put it together and say, all right, this length, that's T, that's TA. And what is it? It's going to be this plus that. This is gamma T prime A. And this, T question mark, is beta gamma X prime A plus beta gamma X prime A. And we've done it. That's a formula for the space-time coordinates of this event. We imagine that we knew the primed coordinates, and we could then figure out from the primed coordinates what the unprimed coordinates are. So we've derived the Lorentz equations. Here they are. So let me say one more thing, and then I'm going to just write this in a slightly different form. So note that the choice of event A is completely arbitrary. I could have put A here, or here, or here, or anywhere, and the geometry and the algebra would work out the same. So I can remove the subscript A from X and T here, and just say that this tells me how to go for any event, anywhere here. This tells me how to relate the primed space-time coordinates to the unprimed space-time coordinates. So dropping the A, and then I'm going to factor out a gamma, because there's a gamma in both of these terms. I end up with this. So this is a standard way of writing on the Lorentz transformations. X is gamma X prime plus beta T prime. T is gamma beta X prime plus T prime. Often, we're interested in these formulas in the other way around. So this you'd use if you know X prime and T prime, and you want to figure out X and T. This you would use if you know X and T, the measurements, the space-time coordinates of an event in the at-rest reference frame, in Anna's reference frame, and we want to know, all right, what would the space-time coordinates be for that same event in the primed frame, in the moving frame, in Beowulf's frame. So these equations are like a pair of bilingual dictionaries, translating from primed moving Beowulf into unprimed at-rest Anna, and vice versa. These are sometimes called the inverse transformations, and these sometimes called the direct. These names aren't important, and I don't want you to think of these as two separate sets of formulas. They're the same thing. So this is what we derived, and you get from here to here by doing algebra. So you just take this system of equations, you solve for x prime, t prime, and you get this. And you can go back by doing the process in reverse. So these equations contain the same information, we just use algebra to write them in different ways. All right, so lastly, as I said before at the beginning of this series of videos, the Lorentz transformations, it's this dictionary between two reference frames, and it's the relativistic version of the Galilean transformation equations, which we had, which were these quite a while ago, I think in the very first unit of the course. So x prime is x minus beta t. X prime is x minus beta t, so similar, it's just this gamma factor, this sometimes called a Lorentz factor, that sort of is stretching out space and time here. And then time, in the Newtonian or Galilean world, like time is time. What do you mean? It'd be crazy for observers to disagree on time, because time is just something external that is what it is. In Einstein's world, in our world, that's not the case. And time transforms in a way similar to that which space does. So in the next video, I'll work through an example using the Lorentz transformations.